History of porcelain, China and Europe. Earthenware were made by Chinese artisans fired in primitive kilns at 900 degrees Celsius, transforming clay and mud objects into delicate and functional pieces of transparent porcelain, but it was still porous and couldn't hold any liquids. About 100 BC, Chinese discovered how to produce more refined pieces fired at a higher temperature, created a stronger and more solid and sealed water stoneware. About 1000 AD, Chinese credited for the development of porcelain, also known as China stone or Chinaware, a strong, functional, transparent containers with a few millimeters thick walls were produced. The terms China or porcelain is still used today to refer to high quality ceramics or porcelains. The composition of China porcelain contains 50% clay, kaolin or hydrated aluminum silicate, 20 to 30% feldspar, sodium and potassium aluminum silicates, and 20 to 25% quartz or silica. Early European ceramic products failed to reach the quality, strength, and translucency of fine Chinese porcelains. In the 18th century, ceramics were still not recognized as a material of value, and those products are becoming closer to the porcelain from China. In 1728, Pierre Fauchard, a French dentist, regarded as the father of modern dentistry, published a book titled The Surgeon Dentist, where he described the use of the porcelain for constructions of dentures. In 1788, Dubois de Chemin patented his formulation of mineral paste and published a pamphlet on his work using the Alexis de Chanteau inventions of material paste, which concentrating on improved color, dimensional stability, and attachment to a denture base. 1888, Giuseppe Angelo Franzi, Italian dentist, developed a method to mass-produce individual porcelain denture teeth with platinum pins in the back of the teeth soldered to the metal denture base, referred as a terrometallic incorruptible or terrometallic teeth. In 1837, Claudius Ashe, an English goldsmith, began manufacturing fine porcelain teeth, also developed tooth teeth, an artificial tooth that could be placed over the post of complete or fixed partial dentures. In 1766, dentistry is brought to colonial America. In 1770s, Paul Revere makes dental appliances in Massachusetts. He is also known as the first U.S. dental technician because of his writing has shown that he's made teeth and sold them to the dentist. In 1785, Dr. Greenwood introduced porcelain teeth in the U.S. and invents foot-powered drill in New York City. Also, he made some of the George Washington dentures, which the base was wood, mahogany plates, and teeth were made from animal or teeth or ivory. In 1817, Antoine Plantot, a French dentist, introduced individual porcelain teeth to America. Around 1830, Samuel Stacont, a Philadelphia jeweler, was first to mass produce porcelain denture teeth in U.S. In 1838, Dr. Elias Willman, a Philadelphia dentist, enhances the formula and brought the translucency and tooth color to the dental porcelain. In 1887, Dr. Stowe and Eddy opened his first lasting commercial dental lab in Boston, Massachusetts. Later, he opened another lab in New York City. In 1904, George Weyrecht developed the procedure for one-piece gold casting. In 1907, William Taggart invents the Lost Wax casting machine. In 1944, the introduction of high-fusing porcelain, 2400 degrees Fahrenheit, and today are used only for denture teeth. 1946, first dental technology program created in New York Institute for Applied Arts and Sciences. In 1950, the number of enrolled students were 141 male and 3 female dental laboratory students, and today it's known as New York City College of Technology in Brooklyn, New York. 1949, Dentist Supply Company of New York. It's a company that took place that was it's a company that took place in 1899, and today it's known as Dentsply. Further enhanced translucency, improved color in dental porcelain. Today, Dentsply it's in New York, Pennsylvania, and offer its dental museum tours. Since then, many individuals and companies have contributed to the development of modern ceramic, metal ceramic, and all ceramic restorations. 1886 to 1888, Dr. Charles Land, a Detroit dentist, patented the process of fusing porcelain to a thin platinum foil, mechanically adapted to the foil to the die, also known as enamel caps or jacket crowns, using a gas furnace, which was a totally new method at the time when the porcelain teeth were used only with dentures. Land also developed low-fusing porcelain to be used on porcelain jackets. However, he faced a lot of difficulties with the material since high levels of borax and pulverized glass contributed to the degradation of restoration in the oral cavity. Land also was a stringent advocate of the conservative dentistry, stating that in nearly all the modern system of crown work, there seems to be too much good tooth material cut away, and I think careful investigation will demonstrate this new process to be far superior, making it possible to save the greater portion of the crown, is not being necessary to cut beneath the gum. In 1905, Land was named Father of the Porcelain Dental Art. Land metal and porcelain crowns become precursors to the modern-day metal ceramic restorations. In 1950, reports of a successful pairing of porcelain fused to gold for fixed restoration. In 1956, Dr. Charles Brecker published The Porcelain Baked to Gold, a new medium in prosthodontics, and was published in the Prosthetic Journal of Dentistry, most widely referenced article in regard to the porcelain fused to gold restoration. Brecker cast a gold crown or a thimble to a platinum matrix, very thin, burnished to a die. Then a platinum foil gold strap structure was returned to a prepared tooth to check the fit and make adjustments. Upon returning to the lab, casting was cleaned with water and dried in the furnace to remove contaminants from the surface. Then bonding agent was added to and fired at 982 degrees Celsius. And then 2 thin layers of opaque were applied to bond and mask the metal look of the platinum foil. Afterwards, the body porcelain and the incisor porcelain were applied, shaped, and fired to complete the process. Because of the difficulty in casting early platinum iridium and platinum alloys, the resultant substructures left much to be desired in terms of the fit. In 1962, Weinstein, Katz, and Weinstein patented an improved dental porcelain for gold-based alloy. In 1965, McLean and Hughes developed the aluminous porcelain that is used today in making porcelain jacket crowns. 2003, large lab productions in over 6 months period accounted for 65% of the porcelain fused to metal and 25% of all ceramic restoration. In 2017, the number grew for the all ceramic restoration to 70 to 80%, and also was reduced for the porcelain fused to metal from to 20 and 30%. So the all ceramic restoration system uses different type of ceramic materials such as silicate ceramics, which can include feldspathic ceramics and glass ceramics. Then we have glass infiltrated ceramics and oxide ceramics, which are densely centers, and those are mostly used for CAD/CAM restorations. Dental ceramics are non-metallic inorganic structures primarily containing compounds of oxygen with one or more metallic or semi-metallic elements such as aluminum, barium, calcium, cerium, lithium, magnesium, phosphorus, potassium, silicon, sodium, titanium, and zirconium. Ceramics are composed of metallic and non-metallic elements that form crystalline or non-crystalline compounds. Porcelain fused to metal can use precious or semi-precious and base dental alloys for substructures such as coping and framework. And the new metal for framework is titanium because it's a light material, it's very strong and biocompatible. All ceramic materials are used as monolithic or as a substructure or framework. And they can include silicate ceramics, feldspathic ceramics, glass ceramics such as lithium disilicate, for example, the Empress and Emax system developed by the Ivoclar Vivident company, glass infiltrated oxide ceramics. The common term used for the metal and porcelain restorations are porcelain fused to metal, PFM restorations, ceramo-metal restoration, porcelain bonded to metal, crown, porcelain veneer crown, metallic ceramic restoration. All ceramic restorations include laminates, veneers, luminaries, porcelain jacket crowns, pressable ceramics, CAD/CAM restorations. The hardness and coefficient of thermal expansion. So each substance, each material has a certain strength and a certain hardness number. And the Knoop hardness number, it's a test for mechanical hardness used in particularly for brittle materials such as porcelains or ceramics. And the Brinell hardness number, it's a test to determine the hardness of metals and alloys by pressing a steel ball into the metal and measuring the resulting indentation into the metal. So for the porcelain, the Knoop hardness number it's 460, the Brinell it's 405. For the enamel Knoop number it's 345, Brinell it's 300. The dentin Knoop number it's 68, Brinell it's 48, and the plastic that's just as a comparison. Plastic is very weak, so the Knoop number it's 20, and the Brinell number is 15. Coefficient of thermal expansion, it's measured in parts per million degree Celsius. And the human dentin, the coefficient of thermal expansion, it's 11.4. For the enamel, it's 12.0. For the porcelain, it's between 14 up to 15.0. For the composite, it's 30.0, and the crystal cobalt or the plus composite is 24.7. Manufacturing dental porcelain. Vitrification and devitrification. Vitrification is the development of porcelain that resembles glass. It is important to note that vitreous or mature porcelains look like. Mature porcelain exhibit maximum shrinkage. The surface is completely sealed and the surface detail is slightly rounded. Vitrification occurs when the firing sequence is interrupted. When this occurs, the porcelain tends to crystallize, making it difficult to form a glaze on the surface. Fritting. Components are mixed together in the powder form, heated to a temperature higher than used in the laboratory. They are melted together and then quenched in water. It cracks and it fractures to form the frit, where the powder of the porcelain is made. A sintering is the process describing the firing of the porcelain powder. It's heating until it's fusing together into an amorphous solid. Basic composition. Low-fusing dental porcelain can be divided into two groups, feldspathic and aluminous porcelain. Although different in their specific makeup, they share common feldspathic glass fleet. Um, Specific ingredients comprise dental porcelain, and the following ingredients can be used to provide the physical properties of dental porcelain. Glass formation. The principal element of glasses is oxygen, which form a stable bond with the silicon to produce silicon oxide tetrahedra. Also, this is called the silicate, common known by another name, sand. Silicon is the major glass formation oxide in dental porcelain, but boron and aluminum may also be used. Fluxes or alkali. Fluxes are added to the basic silicon-oxygen network to lower the softening temperature and increase the thermal expansion of glass. Potassium, sodium, and calcium oxides are the glass modifiers used as fluxes. Intermediate oxides. Aluminum oxide is the most common intermediate oxide used to increase the hardness and viscosity of porcelain. Then the porcelains might maintain their shape and not slump when heated. Coloring and opacifying agents. Presently, the porcelain fleet lacks the color to stimulate the denture and enamel shades of the teeth. Therefore, color pigments such as metallic oxides and opacifying agents such as cerium oxide, titanium oxide, and zirconium oxide can be added. Highly glazed porcelain is one of the materials most compatible with the oral tissue and one of the most aesthetically pleasing of the dental materials. It is used for denture teeth, facing, or veneers, complete crowns, and veneer-fixed prosthodontics units. Porcelain does not have the crushing shear strength of a cast metal. It's weaker, but when it's used in the proper bulk, with the adequate support, it's very satisfactory for dental restoration. Dental porcelains are classified according to the fusion temperature. High fusion temperature between 2350 to 2500 degrees Fahrenheit are used for denture teeth. Medium fusing temperature between 2000 and 2300 degrees Fahrenheit are used for porcelain facing. Low fusing temperature 1200 to 1950 degrees Fahrenheit are used for crowns and veneers. All dental porcelain used to fabricate porcelain veneers or complete porcelain crowns fall into the low temperature range and those classified as low fusing porcelain. Glass properties. Dental porcelain is basically a glass. When heated, it can be shaped and molded into a variety of things. Glass is physically supercooled liquid rather than a solid. However, ordinary glass must be modified and carefully compounded before it can be added as dental porcelain. The composition of porcelain is carefully controlled to modify the physical properties of the glass, both in the molten and solid form. These properties include viscosity, melting temperature, chemical durability, thermal expansion, and resistance to devitrification. The temperature conversion formula. So when we want to switch from Celsius to Fahrenheit. Okay, so this is the formula. So to find out the Fahrenheit, we multiply 1.8 times the Celsius temperature plus 32. And we find out the Celsius temperature. The firing temperature for the low fusing porcelain, or majority of the porcelain layering porcelain used today. Today gas is 1950 degrees Fahrenheit and vacuum opaque 1850 degrees Fahrenheit and vacuum body or 1750 degrees Fahrenheit and vacuum and glaze 1650 degrees Fahrenheit, no vacuum. Another type of low fusing porcelain is lucid porcelain used with pressable porcelains. Lucid reinforced ceramic powders are pressed to form ingots, which are the basis for all ceramics restoration. This system uses a lowest a wax technique associated with conventional metal ceramic restoration. After burnout, the ceramic ingot is heated to a softened state and pressed into the mold. Lucid reinforced restoration gave a very aesthetically pleasing result with necessary strength for veneers, single crowns, and onlays. Porcelain components. The porcelain powders. The manufacturer supplies feldspathic porcelain powders in the following four basic forms. Opaque porcelain. This porcelain contains a larger percentage of opacifying agents such as zirconium and tin oxide, and it's quite opaque. It is used to mask out the color of the underlying metal. Dentine or body porcelain. This porcelain matches the gingival two-thirds of a tooth. Enamel or incisor porcelain. This porcelain is very translucent and it's used to overlay the dentine porcelain to match the incisor shade of a tooth. In addition to the different porcelain powders, each manufacturer supplies a multitude of tooth shades. Even then, it is extremely difficult to make a complete match without the aid of stains or color modifier. Shoulder porcelain. This porcelain is used for the facial margin area to provide an aesthetically pleasing alternative to the metal color. It is available in different porcelain shades to match the dentine and enamel components. Stains and color modifiers. The stains and color modifiers supplied in a kit of dental porcelain are made the same way as the concentrated color frits used to color the porcelain powders. A color modifier is used intrinsically internally to obtain gingival effects to highlight the body colors. A stain is more concentrated than a color modifier, and it's used for external coloration. Because stains are applied to the surface of fire porcelain, they are usually mixed with low-fusing air-fry porcelain. This mixing allows the stain to fuse to the porcelain at a low temperature. Stains are used to color correct or to alter shades and characterize porcelain restorations. Color. Color is defined as the visible light is the range of the electromagnetic spectrum that is visible to the human eye. The visible light range includes violet, blue, green, yellow, orange, and the wavelengths or spectrums. Color is defined as the physical modification of light by colorants observed by the human eye and interpreted by the brain. Dimensions of color. Color can be described by its dimension, hue, chroma, and value. Hue denotes the name or type of the color. For example, red, orange, and blue are all the names for the color. Chroma is the amount of saturation of a hue. For example, an object is intensely red. It's higher in chroma than a pale pink. Value, sometimes referred as the brightness or reflectivity, can be defined as the relative whiteness or blackness of a hue. High value is more white or reflective. When relating to a black and white photograph to describe value, a light blue object next to a tan color object might appear as identical levels of gray. Value is probably the most important dimension of color to the dentist and technician. If the value of a restoration and the teeth match, small differences in the hue and chroma will not usually be noticed, but a crown of higher value will be more reflective and readily visible. Subtractive color system. The system is used with pigmented objects and it's used in characterization of fixed prosthodontic restoration. The three primary hues are red, yellow, and blue. Secondary hues are produced by mixing primary hues. They are orange, green, and violet. Complementary colors. Any hue that is opposite another hue on the color wheel is called a complementary hue. Orange and blue and yellow and violet are the two most common complementary color relationships used in reference to fixed restorations. Translucency. Ceramic materials are translucent like the natural teeth. Crystals reflect incident light, direct the coloration into the deeper layers, and together with the veneer in porcelain provide the foundation for outstanding aesthetic. Fluorescence occurs in a dark environment when the shortened wavelengths of ultraviolet light are reflected towards the viewer as blue or bluish-white light. Dentin exhibits more fluorescence, as does the enamel. Opalescence. There must be sufficient daylight for light waves to be reflected in two ways. Lower energy light is reflected back towards the viewer as blue or blue-white wavelengths. At the same time, higher energy light wave pass through the translucent material and appears to observer as orange, yellow, or orange amber. Opal effects have to do with the light scattering abilities of translucent porcelain. Therefore, opalescent formulations are typically found in an enamel and translucent porcelain powders. Selecting a shade. As minimum, the dentist will select the shade for the restoration and include this information on the prescription form. The technician will then interpret the prescription and make the restoration duplicating the shade selected. Shade selected is the dentist's responsibility, but when it's possible, the individual who will make the restoration should be involved in the selection process. Whether selecting a shade or comparing the restoration to a shade tab, the following principles apply. Take the shade in a neutrally colored room. Once satisfied that the value is correct, try to determine the dominant hue of the tooth. For the last comparison, determine the chroma. The selected chroma level should be closely correspond to the previous value selection. If no satisfactory shade match is available, select the shade tab that is higher in value and lower in chroma. Low fusing porcelain system. The basic types of porcelain system are feldspathic porcelain used in veneering metal substructures, natural feldspar is any group of minerals, principally alumina silicate of potassium, sodium, and calcium. Natural feldspar contain most of the elements needed for glass making. Glass fluxes such as boric acid are added to lower the softening temperature of the glass. This mixture can be fritted at a specific temperature to obtain the desired porcelain frit. Feldspathic porcelain are used in metal ceramic crowns, and they have a firing range of between 900 and 960 degrees Celsius. Aluminous porcelain used in making of the porcelain jacket crowns. The addition of pure aluminum to the feldspar flux masks greatly strength of the porcelain. Alumina is the only true crystalline ceramic used in dentistry. It is the hardest and probably the strongest oxide known. Aluminium porcelain is 3 times stronger than feldspathic porcelain, and it has 6 times its crushing strength. Unfortunately, added alumina also decreases the translucency. The 3 main types of aluminous porcelain include high-strength core material containing as much as 50% pure aluminum crystal, dentin containing 5 to 10% aluminum crystal, and enamel veneer powders. The core build-up strengthened all the ceramics crown, much the same as the metal substructure, but to a lesser degree. Advantages. It's color stable, biocompatible with the soft tissue and tooth structure, is resistant to sudden thermal changes, it is strong, non-toxic, closest material available to mimic nature, and very good resistance to abrasion. Disadvantages. Matching colors might be difficult for a beginner. Technician restoration might be constructed outside the mouth and cemented when it's completed, and require multiple appointments or doctor's visit, and will abrade acrylic and natural enamel because aluminum it's a little bit stronger than the natural tooth structure. Metal ceramic restorations. A metallic ceramic restoration is one in which veneer porcelain is bonded to the underlying metal substructure. This type of restoration enabled the dentist to provide the patient with the aesthetic and biological advantages of porcelain plus the fit, strength, and durability of a ceramic alloy. Also, porcelain is impervious to mouth fluids, color stable, resistant to abrasion, and cause minimal tissue reaction. Physical characteristics of metal ceramic system. Strength of the bond. The role of each bonding mechanism between porcelain and metal is not clearly defined. Three factors influence the bonding of porcelain to the metal. Chemical bonding that occurs when oxide, primarily thin oxide on the metal surface, fused with the porcelain during the firing. A compression bond exists when the cooling metal shrinks, drawing the porcelain together and placing the veneer in a state of compression. The metal substructure should be designed to take full advantage of the compressive nature of the porcelain. A mechanical bond results from the gripping action of the porcelain that has solidified in the microscopic grooves and undercuts of the metal surface. The bond strength of the porcelain fused to metal is greater than the tensile strength of the porcelain itself. A break should occur through the porcelain before the porcelain its metal pull apart. Coefficients of thermal expansion. The success of using one manufacturer's porcelain system with another ceramic alloy might be measured in terms of their coefficients of thermal expansion. The coefficients of thermal expansion of the porcelain and the metal must be relatively close, and if the porcelain is to remain firmly bonded after the completed restoration has cooled. Although the expansion coefficients of both the porcelain and the metal are similar, they are not the same. Porcelain is stronger where it's compressed. Manufacturers deliberately lower the coefficient of expansion of the porcelain slightly in relation to the metal. The porcelain expands or similarly shrinks less than metal. After firing and subsequent cooling, the porcelain is bonded to the metal in a state of compression. If the opposite condition exists, the porcelain after cooling should be in a state of tension and the veneer will likely crack. It is for this reason that the porcelain and alloy chosen should be a compatible system. Strength of the substructure. When a porcelain veneer is bonded to the metal, any deformation of the metal may cause the brittle porcelain to fracture. Metal frameworks must be strong enough to resist any deformation and under the occlusal forces. An alloy strength does not depend solely on how its molecules are put together. Strength is also depending on the bulk and design of the metal framework. As the length of and the span increases of fixed partial denture must have a thicker cross section, and the thickness increase must be in line with the occlusal loading. In designing posterior fixed partial dentures with veneer pontics, one reason for covering the occlusal and tissue contacting surfaces with the metal is that the correspondingly greater bulk of the metal will increase resistance to deformants and decrease the possibility of porcelain fracture. Melting range of ceramic alloy. Most low-fusing porcelain mature between 850 to 1065 degrees Celsius. Because of the melting range of the conventional golds used in dentistry, it's approximately the same temperature. It is necessary to have an alloy with a higher melting range to withstand the firing temperatures of dental porcelain without deforming. Several ceramic alloys are formulated with a casting range between 1150 and 1360 degrees Celsius. The technician can bond low-fusing porcelain to these ceramic alloys without any deformation of the framework. The thickness of the veneer. The combined thickness of metal and porcelain on the facial surface of metal ceramic crowns should be at least 1.2 to 1.5 mm thick to meet the minimal strength and shade requirements. There should be at least 0.3 mm metal thickness on the porcelain veneer areas to keep the substructure from flexing during the seating or occlusal load, thus fracturing the applied porcelain. The opaque layer needs to be 0.1 to 0.2 millimeter thick to perform its masking function. The dentin and enamel porcelain should be a minimum 0.8 thick, with 1 millimeter being ideal to reproduce the desired shade. More porcelain might be needed in the incisal portion because of added translucency necessary in that area. Factors in substructure design. To a great extent, the shape of the metal substructure seriously affects the stresses that develop in the porcelain. As being fired, porcelain tries to become a sphere. This results in the porcelain drawing to the metal substructure, and when the restoration has cooled the porcelain, it's in a compressive state. If the metal surface is sharp or uneven, tensile stresses are created in the porcelain as it cools, and it might cause the veneer to fail. The primary bond between porcelain and metal is a chemical in nature, but mechanical bond is also important in this bond. Bond strength overall seem best when the porcelain-bearing metal surfaces are gently rounded. Avoid producing corners, angles, points, or deep concavities on the porcelain-bearing surfaces. Sharp angles and points will create stresses in the porcelain, causing to fracture. Deep concavities are a problem because the porcelain is likely to shrink away from this area during the firing towards its greater bulk or thickness. Due to the tenacious bond strength between porcelain and metal, mechanical retention in the form of beads, lugs, or peripheral boxing is not required, and if present, will make the porcelain more susceptible to fracture. The technician can place the required metal and porcelain thickness on a stone die regardless the amount of tooth reduction done by the dentist. However, if the tooth normal contour is to be restored, the dentist is obligated to reduce the facial surface of the tooth at least 1.2 millimeter to ensure there is enough minimal thickness of the metal for the metal and porcelain. Pontics should be made to be bulk. On the pontic, it's composed of metal evenly veneered with 1 to 1.5 millimeters of porcelain. Metal ceramic frameworks should be made so the porcelain can be uniformly applied in a thickness that doesn't exceed 1.5 millimeter on the facial or 2 millimeter on the incisal. Try to keep the porcelain to a minimum thickness without sacrificing aesthetics. A thin, uniform thickness of the porcelain supported by a rigid substructures offer the most strength. The relative thickness of the metal substructure, opaque dentin, and enamel porcelain depend on the type of ceramic alloys and the porcelain used. For example, metal substructures made from high gold content alloys need to be at least 0.5 millimeter thick to adequately support the porcelain. The minimum thickness listed above are not absolute and will not apply to every given case. Strength requirements also depend on the design and extent of the restorations. Cervical collar. A cervical collar of metal is recommended for strength and support of the porcelain in the shoulder area. With bevel shoulder preparation, the width of the facial bevel determines the width of the cervical collar. A 1 millimeter wide bevel requires a 1 millimeter wide cervical collar. At minimum, provide a 0.5 millimeter cervical collar as a routine practice. Anterior design. Because of the occlusal contacts should not occur at the metal ceramic junction, the contact should occur either on the metal framework or on the porcelain. Keep the metal ceramic junction well away 2 millimeters from the contact point. If you don't, the metal might flex and cause the porcelain to fracture. Posterior design. In the maxillary arch of a premolar, the metal ceramic junction is located across the buccal triangular ridge. If the metal ceramic junction is placed too close to the fossa, the porcelain is fracturing. Removing contamination. Before applying the layer in porcelain, the metal framework must be decontaminated. A high gold content alloy framework has been finished on a metal die, copper, silver, or amalgam. Boil it in nitric acid for 1 minute and then pickle in the hydrochloric acid. This procedure eliminates any possibility of contamination from the metal die. If using a white ceramic alloy, consult the manufacturer instructions for each behavior in acids. Porcelain application and firing. Opaque porcelain. Opaque porcelain serves a threefold purpose. It masks or hides the color of the underlying metal. It stimulates the dentin of the natural tooth and complements the dentin-shaped porcelain. And it combines with the metal surface oxide to form a powerful bond. Dry the opaque in front of an open furnace door or throw the moisture away with the tip of the facial tissue. Remove any opaque porcelain from the inside of the casting or the non-porcelain bearing areas. Firing. Place the casting on the firing platform, insert the crown into the furnace and start the vacuum pump following the manufacturer instruction. In most of the cases, a second coat of opaque porcelain is necessary. Fire at the same temperature. The casting or opaque should now measure at least 0.5 mm in thickness, allowing 0.2 mm for the opaque layer. Porcelain application. Condensing porcelain. The process of packing the particles together and removing the water is known as condensing. The methods used to condense the raw porcelain mass and your experience as a ceramist will determine the quality and the amount of shrinkage of the pressed veneer. Porcelain will always shrink towards the greater the thickness, that is, towards the incisal and interproximal at the suprabulge area. Methods of condensing the porcelain: vibration by serrating or tapping with an instrument, perform capillary action by blotting from the lingual surface, perform pressure packing, continuing by whipping or brushing the surface with a large soft brush to fill the surface voids and remove any loose particles. An alternative to the full coverage or ceramic crowns is a porcelain laminate veneer. Veneers are a thin shell of porcelain covering the facial surface of the prepared tooth. Veneers offer the same aesthetic advantages of the all ceramic crowns with a more conservative preparation. Also, they can be used to cover discoloration on enamel effects, close diastema, repair chipped teeth, and correct slightly misaligned teeth. Many techniques are available for producing porcelain laminates veneers, including the platinum foil technique, refractory technique, and pressed ceramics. Refractory technique: masterclass preparation for the impression in die stone and allow to the final set. Trim the cast to standard dimension and remove any soft tissue interference from the margins and interproximal areas. Mark the margins with a red wax pencil and apply die spacer to within 1 mm of the margin. If possible, use a removable die spacer to allow for easier sealing of the finished veneers on the master cast. Ensure the removable die spacer is compatible with the duplicated material used in the refractory cast fabrication. Refractory cast fabrication box the master cast to include at least one adjacent tooth on both sides of the prepared tooth. Using high quality duplicated material, make a mold of the box portion of the master cast. After duplicating material has set, remove and inspect the impression for any voids, particularly around the margin. Pour the mold with refractory material designed for the use of porcelain veneer system. Pay close attention to the manufacturer directions. Carefully remove the refractory cast from duplicated material. Inspect the refractory cast for voids and any critical areas. Trim the excess material from the base of the cast, ensuring the base is smooth and flat. Pin and base the cast using the reverse pin technique. Seal the bottom of the cast with a die hardener, waterproof sealant. Drill 2 holes in each of die using a Pindex or parallel pinning machine. Insert the dowel pins into each hole and um, when using this technique, it is easier at this time not to separate the cast into the individual sets. The cast will be sectioned into individual dies after the first firing and contouring had been accomplished. This method increases the stability of the dies during the porcelain application and contouring steps. Cast preparation. Degas the refractory cast in a burnout oven, following the manufacturer direction for the refractory material. After degassing, the refractory cast should be whitish in color. Gray or black areas indicate the need for additional degassing. First soak of the refractory cast in distilled water is to prevent the porcelain from drying out quickly during application. Repeat the soaking process after firing and before each new layer of porcelain is applied. Mix and apply a masking porcelain layer. Opacity and depth will vary depending on the aesthetic requirements. If you are covering stains or discolored teeth, more masking porcelain is needed. Then you are for the cases where you are closing diastema. Dry and fire the porcelains following the manufacturer instructions. Shape the mamelons with a brush if desired. Apply incisor porcelain from the incisal edge, tapering into the body porcelain to create natural dentition enamel blend. Cut through the embrasures with a sharp instrument to separate the veneers. Fire the veneers in a porcelain oven using the manufacturer's guideline for the time and temperature. Contour the porcelain with a medium fine grit diamond stone. If the porcelain additions are necessary, clean the veneers and then apply porcelain and fire it in accordance with the manufacturer guidelines. Selection of the cast into individual dies by using a disc to cut section of the dies that are to be removable. To add porcelain, remove the glaze and clean the restoration. Then apply the same porcelain powders originally used during the initial application. Be sure to add enough porcelain to allow for recontouring. The porcelain addition must be meticulously applied, shaped, and well condensed. Fire the porcelain addition under the vacuum at a slight lower temperature. After all correction and contouring are complete, stains it's needed and glaze. Divest the complete restoration by removing the bulk of the refractory material from the inside of the veneer with a number 8 burr. Be careful not to touch the margins. Finish cleaning the refractory from the inside of the veneer with a 25 micron aluminum oxide or glass beads at 40 psi. Seat the veneer on the master cast by first carefully removing and any overextensions of the margins with a rubber wheel. If possible, remove the die spacer from the cast. Etch the veneer by first covering exterior surface with wax and attaching sprue wax to the facial surface to act as a holding device while etching the process. After the etching process is done, clean the veneer with distilled water in the ultrasound unit. So this is the fabrication of the refractory model. So there is a difference between the foil technique and the refractory models. Both of them can be used to fabricate porcelain to foil or porcelain jacket crown. The foil, like we said, it's a material that can be adapted to the die. It's a thin material that can be cut and adapted to the die, especially to the margin. And then porcelain is applied. Once the porcelain is finished, including the staining and the glazing, then the foil can be removed from the veneer, and then it will be all porcelain. It's the same case for the porcelain jacket. The refractory model method, it's includes the fabrication of model that uses a material. Usually we pour the model in die stone. This is a refractory model. which is more like investment material that can be put in the oven. And the porcelain, the baking porcelain, can be baked directly on the model, so we don't need any foil. That's the difference between the two methods. Okay, so this is how the foil, the laminate, it's built up on the model, and then the model is just actually the veneer is just removed from the model, and the fit is perfect. Okay. These are some of the few key terms from Phillips Science of Dental Materials. So some of the terms that we need to be aware of are the bonding mechanisms by which a dental porcelain fuses or it's glued to a metal substructure. Oxidation process by which a cast metal substructure is heated, treated in porcelain furnace to elevated temperature, typically in reduced atmosphere or vacuum, to produce an oxide layer for porcelain bonding and to cleanse the porcelain bearing surfaces of contaminants. Also, this process is also known as degassing. We talk about the coefficient of thermal expansion, where especially for a porcelain fused to metal restoration, the coefficient of expansion have to be similar of the metal and the porcelain. If the coefficient is a little bit different, the gap between them is too big, that means either the porcelain is going to break or the bonding between the porcelain or the metal is not strong enough. Green state refers to especially when we mill different type of CAD/CAM ceramic materials. And that implies the material is a little bit softer and it has to go through a sintering process or vitrifying to be fired and to become strong and have the color or the shade that it's supposed to have. Natural glaze is a superficial layer on a ceramics ceramic or metal ceramic prosthesis formed by heating of dental porcelain to form a smooth glassy layer. Overglaze, a coating of glass formed by fusing glaze particle on the ceramic surface. All right, and those are some of the porcelains that we're using. Please take a little bit of time to read through this and to understand the role of each porcelain. And that's about it. Thank you. If you have any questions, please ask. Thank you.